Hey everyone, in this video we're going to cover analysis of variance, or oftentimes abbreviated ANOVA. And so what ANOVA is the analysis of a quantitative variable when you have multiple ones. So last time we did goodness of fit, which was when you have multiple proportions, right? More than two, at least three proportions. Proportions is when you have a categorical variable. So here, ANOVA is when you have quantitative variables and you have more than two samples, so at least three. So we are going to look at this example, the well-being index, and I'm going to state it again below, but essentially we want to see the well-being index is a way to measure how people are faring physically, emotionally, socially, and professionally, as well as to rate the overall quality of their lives and their outlooks for the future. And we're going to look at the data that is stored in StatCrunch that tells us the well-being index scores for a sample of states from 4 different regions of the United States. And we're going to do our analysis at the 0.05 level of significance, so 5%. And we're going to try to figure out what the claim is and do our hypothesis testing. But what does that mean? Do a hypothesis testing for, right, we have 4 different regions. So that means we're going to have 4 different means. So for a one-way ANOVA test, the null and alternate hypotheses are always similar to these statements. So this is how you kind of want to write them. The null hypothesis, remember, it always has the equality statement. So here the null is all the means are the same. So everyone has the same average index. So all the 4 regions have the same well-being index on average. So all population means are equal, and the alternative is the claim, right? That the mean score is the same for all regions. That's the claim. So that's the null hypothesis. So here, the alternative is the opposite of the null. So the opposite of saying all are the same is at least one of them is the same. In symbols, this is pretty difficult to write because you will have to then say, like, if one of them is the same, right, mu1 could be equal to mu2, or mu1 is mu3, or mu1 is mu4, and so on. And so you have to do it for all of them. So for these, goodness of fit and ANOVA, it would be really hard to write it in symbols, so you will just have to write it in words. And just to show you real quick what it would be like for our example. So if I have my example here, then the null hypothesis will be that they're all the same. So I'm going to have H null will be that mu1 equals mu2 equals mu3. We have 4 regions, so it'll be the average of each region. The alternative hypothesis, if I was going to write it in symbols, it would be, right, the complement of that. So the complement of all are the same is at least one is different. So either mu1 is not equal to mu2, right? So those are not the same, or mu1 is not equal to mu3, or mu1 is not equal to mu4, right? Or, and you can kind of go down the line, right? Or mu2 is not equal to mu3, or mu2 is not equal to mu4, or mu3 is not equal to mu4. So that's what it will, that will be the complement of this, right? This says they're all the same. The complement of they're all the same is at least one is different. So that means that, right, either mu1 is different from the other 3, which is this long sentence in symbols, or mu2 is different from the other ones. We already captured mu2 is not equal to mu1, so you don't have to rewrite it. So either mu2 is not the same as mu3 or mu4, and then or mu3 could not equal to mu4. So this is the part that it gets pretty cumbersome. So instead of writing this all out, imagine if you had 6 averages, right? This will get even longer. So we just say at least one is different from the other. And so that's what I had on the notes, right? At least one of the means is different from the others. So when you have more than 3, it's easier for the alternative to just leave it in words. Now, before we perform a one-way ANOVA test, you must check that the conditions are satisfied. So we're essentially checking that we can use the central limit theorem. So either you have the sample sizes or your samples are coming from normal or approximately normal populations. And the samples must be independent of each other, and each population must have the same variance. So here that this is pretty important for an ANOVA test, that each population must have the same variance. Now the test statistic for a one-way ANOVA is the ratio of two variances. So we look at we'll be using the F distribution. So our test statistic is F equal to the variance between samples divided by the variance within the samples. So what that means is the numerator is the variance between samples. This measures the variation between each sample. And then the denominators depends only on the sample variances and is not affected by differences among the sample means. So essentially, variance between samples, you're seeing how do the means differ, right? So you have, like in our example, we have 4 means. Are they all 4 close together or are they far apart? So that's the variance between samples. Now the variance within samples is talking about each sample themselves. How do the data values in that sample vary from their own mean, right? In our example here, we have 4 regions of the United States. So if I'm looking at, for example, say the Midwest, then the denominator will be looking at how the data values from the Midwest differ from the Midwest's mean, versus the variance between samples will be looking at how do the means from the Midwest and the other 4 regions, so the South, the Northeast, and the West, I have to look at the regions again, vary from each other. So that's kind of what that encompasses. So the ratio between them is what gives us our statistics, and this is why it's called the analysis of variance. We're looking at the variation between samples and then within samples. I won't show you how to do this by hand and giving you all the crazy formulas. We'll rely on technology, and we'll use StatCrunch to perform the analysis of variance. The F distribution is what gives us our test statistic, and so that is a right tail distribution, or skewed right distribution. So the green highlighted region there is our rejection region. So if we have a p-value that falls in there or a test statistic that falls in there, then we will say we reject the null. For hypothesis testing, we're always talking about the null hypotheses. I encourage you to go back and look at the comments that I left for your submission of your hypotheses for the semester project, because there were some that were flipped. You had some of us had the alternative as the null and the null as the alternative. So just make sure you go back and look at the comments that I left. And unless you have multiple means or multiple proportions, goodness of fit or ANOVA, which we're doing ANOVA right now, so I don't think your semester project will include ANOVA, make sure that your alternative, both your null and alternative, are written in symbols. So only if you're using a goodness of fit test, you wouldn't have your alternative written in symbols. But if you're doing 1 proportion, 1 mean, 2 proportions, 2 means, correlation, you should be able to write all of those, both of these, null and alternative, in words and in symbols. All right, so how do you perform a one-way analysis of variance test, ANOVA? Go through all the conditions, verify that the samples are random and independent. In this case, there's no size requirement, but you have to have the normal distributions and that the population variances are equal. You identified your claim, state the null and alternative hypotheses, and I will say both, right, in words and in symbols. Well, in this case, in symbols, the alternative is you always write it in words for just goodness of fit and ANOVA tests. Everything else, you should be able to write them both in words and in symbols. specify the level of significance. So this will always be given to you if you're doing a test or a homework, but for your semester project, you are creating your own study, so you need to decide the level of significance that you are going to use. The standard is the 5% level of significance, but you can choose whichever level of significance you want. Determine the degrees of freedom from the numerator. So this is if we were going to try to find the critical value for 5 and 6 to determine the rejection region. So determine the degrees of freedom for the numerator and the denominator. Degrees of freedom for the numerator are k minus 1, where k is the number of samples. So for our example, we have four samples, so 4 regions, and so we're going to use 4 minus 1. So the degrees of freedom for the numerator will be 3, whereas the degrees of freedom for the denominator is n minus k, where n is the sum of the sizes for each sample. So we'll have to look at what those are. And then you determine the critical value by looking at a table. So let me add that in here. So by looking at the F distribution table, which is, you can find it in your textbook. Determine the rejection region based on that. We won't calculate the test statistic by hand. We're going to rely on StatCrunch for that. And then we're going to look at our p-value and make a decision. Do we reject or fail to reject the null hypotheses? Then we interpret the decision in the context of the original claim. So back to our example. The well-being index is a way to measure how people are faring physically, emotionally, socially, and professionally, as well as the rate of overall quality of their lives and their outlooks for the future. And so we're going to pull the data from StatCrunch. It's called Well-Being Index, and you can find it under our group for StatCrunch. And you'll be able to see the 4 regions of the United States there. So at the 0.05 level of significance, we want to test the claim that the mean score is the same for all regions. So let me highlight that. This is our claim. This is what we want to do a hypothesis test analysis on. So perform a one-way ANOVA to determine the claim. So let's go to StatCrunch. So once you're logged onto StatCrunch, you can come to the StatCrunch home and go to My Groups, and then pull up our group and find the data. So this is usually the most recent data. It is way at the bottom. So here it is, Well-Being Index. So it's on page 2, way at the end. So pull it up. And so here's our data. So we have the 4 regions: Northeast, Midwest, South, and the West. And so only some states in those regions were sampled. And so this is the index, right, for those states in the region. And so then we can find the average of the Northeast, the average of the Midwest, the average of the South, and the average of the West, and then see how close they are. But we are not doing the math by hand, right? Otherwise, I will have to find the standard deviation of each and provide you with all those, like I said, kind of crazy formulas in order to find the F statistics. So we are going to rely on StatCrunch. So we're going to go to Stat, our friendly menu, the one that we use the most to do all our statistical analysis, and we're going to go to ANOVA, analysis of variance, and we're only working with a one-way analysis of variance. If you continue your study of statistics, become a statistics major or get a statistics minor, or you're going into economics, you'll probably have to take more statistics, and you'll then see the two-way analysis of variance. But for this class, we're only going to do the one-way. And then we select in this case, all the columns. Depending on what your data look like, you would choose only the columns that you need to do the analysis of variance on. And we select our 4 columns, and that's it. So we compute. And so here's our result, which gives us a lot. So the nice thing about this is that even though these are smaller samples, I could count them by hand, right? Or I can look at here, 6, 8, 11, I can tell what the sample size is. It gives me the sample size. So the Northeast, there were 6 states that were that we got data from. Then the Midwest, there were 8 states, the South, there were 11 states, and the West, 9 states. And then we have the means for each of those. So looking at the standard deviation as well, right? How are those states compared, like within each sample or in those regions? So the mean for the Northeast was 62.55 and 62.4 for the Midwest. So those are kind of close. But then we have the South, which is 61.67. So those are now farther away. So we have something to go on. And so let's see. So where is our statistic? There's our F statistic, 3.66243. And there is our p-value. So let's look at the F statistic first of all, and let's try to find what our critical value will be. So going back over here to my notebook, now when we have if I wanted to do it by drawing the critical region, then I would come over here and draw my skewed right F distribution, and then try to figure out, okay, what is my critical value? And we find that by looking at the F distribution table with degrees of freedom for the numerator and degrees of freedom for the denominator. Now we did say that degrees of freedom for the numerator were the k minus 1. So k was the number of samples. We had 4, right? The 4 different regions. So 4 minus 1. Oops, 4 minus 1, which is 3. I was already thinking the answer was 3. And then the degrees of freedom for the denominator are n minus 1. I guess I should maybe use a different type of n here for numerator. N minus k, sorry, not n minus 1, where n is the sum of the samples, and then k is the number of samples that we have. So the sample size of each, what did we have? Let's go back to StatCrunch and see. We had n equals 6, 8, so that's 10, 11 and 9 is 20, so 30 is our total n, right? And we have 4 of them. So this will become then 30 minus 4, which is 26. So the degrees of freedom for the numerator are 3, and the degrees of freedom for the denominator are 26. And so now we can look at our F distribution, and you can find this in your textbook, is in the Appendix A for the tables. And we have our level of significance was 0.05. And so we look for, okay, degrees of freedom. Notice that here it says numerator degrees of freedom. And then the vertical one is denominator degrees of freedom. So depending on your level of significance, ours was 0.05, then we are at the correct table. So numerator degrees of freedom was 3, and denominator degrees of freedom was 26, right? So then we're going to go the third column and then 26. So 2.9752. So that will be our critical value. So 2.9752, let's remember that. So our critical value here then is 2.97, what was it? 42, I think. 52. So 2.9752 is our critical value. Right, so that means that this is 2.9752 right here. So this is the rejection region. So now let's look at our statistic. Notice that our F statistic was 3.66. So does that fall in the rejection region or no? It will, right? 2.9756 is here, so 3.66 is over here. So this is our F statistic, which is in the rejection region. So therefore, this will tell us that we reject the null hypothesis. Now, the other way that we can do it is by looking at the p-values. Right? Notice that the p-value here is 0.0231. So how is that compared to our level of significance? When we do it by p-value, now we have our critical value is going to be over here, but the rejection region, right, this area over here is our alpha, and alpha is 0.05, because we were told at the 0.05 level of significance. And so this is our rejection region, is over here. So our alpha is 0.05. Our p-value, what was our p-value? We got 0.0231. So our p-value is 0.0231. So what can you say about this? Do we reject or fail to reject the null? How do we decide? You check, right? Compare the p-value versus the alpha. So 0.0231 compared to 0.05, which one is smaller? The p-value is smaller. So that means that this area, right, the area of 0.02 is smaller than 0.05. So you're going to have the area is within the rejection region. So then we say we reject the null hypothesis. Now, of course, we want to write it in the context of the problem. So we're rejecting the null. Was the null our claim? The null was our claim, right? It says at the 0.05 level, can you reject the claim that the mean score is the same for all regions? So in this case, the null hypothesis was our claim. If it helps you to write claim next to which one it is, that sometimes makes it a little bit better, and then you don't have to go back and read the problem all over again. So with the conclusion, always make sure that you write it in the context of the problem. So in this case, we can say there is sufficient evidence at the 5% level of significance to reject the claim that the well-being index is the same for the 4 different regions of the United States. I guess we should say that the mean or the average well-being index is the same for the 4 different regions of the United States. This is just an example. Of course, you can write it in your own words, but the key thing is to always write your conclusion in the context of the problem. So don't, if you just say, leave your answer as reject the null hypothesis, that's not going to get you full credit. You have to be able to put it in the context of the problem, right? Like on the test, there was the one question, the one that I can't remember is about fathers being involved, right? So if you just say we reject the null, what does that mean, right? So you want to be able to say we reject the claim that fathers, the proportion of fathers is, I forget exactly what the problem was, but you want to make sure that you write it in the context of the problem for every hypothesis problem. So especially as you're doing your semester project, make sure that you follow the rubric that I posted, and that at the end you write your results in the context of your own study, like what was the question that you posed or that you're studying, and make sure that you write your results in the context of that. All right, well, email me if you have any questions.